Good morning, everyone, and welcome to the Cryosphere Pavilion on Thursday, the 10th of November. My name is James Kirkham. I'm from the British Antarctic Survey, and I'm one of the early career scientists helping to run this pavilion this year. Today and this morning, we have a special session about the Arctic Ocean and mid-latitudes. What's up with the weather? Our first speaker will be Bimo Narola, and I'll pass it over now.
Thank you, James. So like James said, I'm Bimo Chaniraula. I'm a cryospheric scientist at Alfred Wegener Institute. And I'm speaking a little bit out of my depth today, but essentially, what do we know about the linkages between ice loss in the Arctic Ocean and the worsening of the weather in the mid-latitudes? So let's first start a little basic. Let's just go to the next slide. Oh, thank you. Awesome. So let's start basic with something that we all know, we've all agreed upon, especially if we're already here, that the global mean surface temperatures have already gone up by about 1.2 degrees above the baseline of 1850 to 1900. In fact, 2020 was the second warmest temperature recorded. And the past decade, the 2011 to 2020 decade, was the warmest decade on record. In the ocean, it's a similar story. It has been accelerating in the last 20 years at all depths, which has already brought about this idea of a new normal, where if we compare the previous decade of the previous 81 to 2010 normal average against the 91 to 2020 normal, we see a very strong warming, especially in the Scandinavian and Central European regions. This new warmer baseline reflects observed changes in the climate. Alongside this global temperature change, what you can also see is that the Arctic is warming at 3 times as fast as the rest of the planet. Here you can see these climate stripes, and these are particularly for the Arctic, and you see how strong the temperature change is right at the end. So this concept is related to what we know as Arctic amplification. And what is Arctic amplification? Here's a little rough summary about it. There are various processes kind of leading into it. Overall, what's happening is that increase in temperature globally is even more pronounced in the Arctic. So there are various factors leading into it. One of the main one is due to the albedo feedback, because the difference in the reflectance, so how white snow is versus how dark the ocean is, means that when you're losing snow and ice from the upper layer, you're absorbing more sunlight into the ocean surface. This leads to a lot of other things, such as a warming in the upper oceanic layer, which gets integrated below, and also a change in the temperature gradient between the Arctic and the mid-latitudes. There are other factors associated with Arctic amplification that I'm not necessarily going to go, but they also affect us, such as more aerosols or reduced stability in the water column, potentially more water vapor and clouds in the upper layer that actually increases the insulation effect from the top. So all this kind of ties in with the fact that in the Arctic, we're losing sea ice rapidly. In fact, if you see compared to the 1980 versus now, we've already lost up to half of the ice extent in September. It's true across the season. In fact, in 2022, which is the blue line, the winter highest ice extent was actually the lowest on record. For the September ice record, it was not the lowest. 2012 was the lowest sea ice extent in the Arctic, but we're right near the bottom. And this again goes back to show, here we have another figure illustrating Arctic amplification. You see that there has been the temperature anomaly is present throughout the globe now, but as we progress further in time, you see that the Arctic is warming especially strong. Um, so yeah, we see this temperature change reflected in another figure here where we're seeing the temperature anomalies in the map, and we see that the peak is located right above where we would expect the peak sea ice to be. And Arctic summer temperatures are off the charts. But then this brings us back to the original question. Is the loss of sea ice also making the mid-latitude weather worse? Now, one potential link is that has been proposed is that a warm Arctic means weaker temperature gradient against the mid-latitude, which leads to a weaker polar vortex. And this is something that we know that a stable polar vortex means that the cold air is contained in the upper latitudes, whereas a weak or wavy polar vortex means that warm air can move north while cold air can move southwards. So this brings a instability in the mid latitudes, which leads to extreme weather events. There's another illustration here of how a strong jet has a more stable jet stream, whereas a weaker jet is this wavy jet stream leads to a further dispersal of the temperature. So essentially, the idea is a warm Arctic leads to a weaker jet stream, which leads to more persistent weather patterns. And this weaker jet stream event has been observed multiple times in the Arctic. So, according to Jennifer, I forgot her last name. That's this. Her, so who was supposed to give the original talk? Her theory is it takes two to tango. What does it mean? It means that when we have in the good old days when sea ice extent was stable, the jet stream was stable between these ridges and troughs going up and down across the mid latitudes. But as we have a decrease in sea ice extent, as the sea ice edge is moving northwards, we're getting a we're getting more variability in the jet stream, where sometimes the ice loss has no effects, whereas sometimes the ice loss is actually causing a weakening pattern and moving the cold air down southwards. So extra heating is intensifying the ridge, making it more persistent in this occasion. This has been shown by various studies already. Strengthened linkages between mid-latitude and Arctic boreal winter is something that is being discussed. However, now this comes to the flip side. The jury is still out on this, and recent research is actually asking if this is a stable effect, or this has more to do with natural variability in this context. So I found that this was the perfect answer for this. The chaotic nature of atmospheric circulation precludes easy answer. So this topic is a major science challenge and is still ongoing. However, this argument is only about the connection between the mid-latitude weather and the Arctic sea ice. We're not putting there's no doubt about an increase in extreme weather cases, and this is widely agreed upon. As you see, sorry, I'm a little foggy in the. And this is the report from IPCC, which shows you an increase in extreme weather events throughout the board. And there are projections by this is from the Met Office UK, which shows you what kind of extreme weather events we're expecting. We're expecting a wetter winter, drier summer, more drought events, but there is rainfall, and when there is rainfall, it is more intense. So to conclude, global mean sea surface temperature has already increased by above 1.2 degrees Celsius, but the change is up to 3 times stronger in the Arctic, especially related to Arctic amplification. The sea ice extent in the Arctic is also declining substantially, particularly in the summer, where it has already halved compared to 1980s. This reduced sea ice cover and the associated ocean heat flux may be causing a weak or wavy polar vortex, which is causing more extreme weathers in the mid-latitude. However, this is an area of ongoing research, so the jury is still out on this link. And I'd like to thank you all for your attention. I'd like to thank Jennifer and Ella for the additional slides. And I want to end with this picture, which is, I think in Arabic, it's called Naboob. It's a strong dust and strong storm event that happened in Arizona 2 years ago. So thank you all. And with that, I'd like to pass the mic to Robbie.
Hi everyone, I'm Robbie Mallet. So we organised this talk as a double act at fairly late notice, and I guess I just want to provide the other side of the argument about this specific topic, about whether sea ice decline and extreme weather are related. Thanks. Because although there's like a very, very clear consensus that the Arctic is warming much faster than the globe, there is a very live and real scientific debate about whether specifically sea ice loss and Arctic amplification are increasing the instances of really cold, extreme weather outbreaks in what we call the mid-latitudes. So by the mid-latitudes, we mean places like the UK, Europe, the continental USA. So this is what the IPCC has to say in its recent report. They say that changes in the sea ice do have the potential to influence mid-latitude weather, but there is low confidence in the detection of this influence for specific weather types. So when we talk about the detection, we're talking about whether we actually see this in reality versus what's happening in our models, which don't necessarily represent reality. And if you would permit me, I would I'll just talk about a couple of key scientific studies that provide the counterpoint to the traditional argument that a rapidly warming Arctic is weakening the temperature gradient, making the jet stream wobblier, looser, and causing more frequent outbreaks in terms of extreme weather in the mid-latitudes. Maybe this will work. Do you know what button it is? All right. Holding the clicker upside down. So the key bit of science in this argument is that on the top we're showing the change in the gradient between the equator and the poles, and it's just blue, okay, and that means it's decreasing, right? So although the equator is much warmer than the poles are catching up, right? And this is what we call Arctic amplification. So and on one axis you've got when you start your study, and on the other is when you end your study. And it's just blue across the board. That's the key message I want to get across here. So the Arctic is warming much faster than the globe. On the bottom row of this, admittedly slightly confusing, but I think super useful slide, is the actual waviness of that jet stream. And you can see that it's a bit of a patchwork of red and blue. And the result of that is, if you're looking at changes in jet stream waviness, it really, really matters when you start your study and when you end your study. And this is how we ended up with this, what we call divergent consensus on this topic of sea ice loss, wavy jet streams, extreme weather outbreaks. So you can see that if you start your observation in 1990, and if you end it in 2005, see a red patch, right? So you see just very clear in the observational records, increased waviness in the jet stream. So you would conclude that because the Arctic is warming faster, and the jet stream is getting wavier in your observational study, that these two are linked, and we can expect in future a wavier jet stream. But as the observational record has lengthened and people have done longer and longer studies, this relationship is weakened essentially. So now imagine a study that starts in 1980 and ends in 2015 or even later. You suddenly find yourself in the top right-hand corner of these plots. So you find yourself in October, November, and December, you find yourself here. And in January, February, and March, you find yourself up here. And you'll notice that in neither of these two bottom row plots do you see a strong coloring, right? So in neither of these plots, if you do the longest possible study of these phenomena, do you find a clear link between Arctic amplification and the outbreak of extreme weather. And this is from Russell Blackport, who's a bit of a powerhouse in this domain of science. So if you are interested in following up, I just Google Russell Blackport. I just wanted to touch on one other, I think, really interesting argument, and I'm more presenting these studies to cue me than for you to dig into the titles too much. But the top is a study that came out in 2014 saying, hey, we actually see less temperature variability from day to day because of Arctic amplification rather than more. And note I said from day to day there, I didn't say extreme events. And I think this is a really nice example of how science works, that this study came out in 2014. And then just last year, we managed to actually attribute an observational trend to the human influence of greenhouse gases and global warming. So to summarize the top study, I want you to just imagine that you live in the UK. I live in the UK, so it's easiest for me. We typically get cold days in the UK when wind and air comes down from the north. It comes down from the Arctic. Sometimes we call it the beast from the east because it actually kind of comes from the northeast. And we get super cold days when we get air from the north. And on other days, we get really warm air when it comes up from the south. It comes up from the equator, the tropical latitudes. So we experience day-to-day temperature variability. And both the air in the south and the air in the north of the UK, they're both warming. Okay, so the temperature in the UK is getting warmer. But what's interesting is that the air in the Arctic is warming much faster than the air in the equator. So the temperature of those cold days when the air comes from the north is actually getting warmer much faster than the temperature of the warm days when the air comes from the south. So if you're an observer in the UK like me, you actually experience warmer cold days, much warmer cold days in fact, and only slightly warmer warm days. So the temperature variability that you experience because of Arctic amplification is lower. So you might expect a more consistent experience basically from day to day and week to week. And that's not to say anything about extreme weather outbreaks. I've already talked about that, but just in terms of what's described here as the sub-seasonal temperature variability in somewhere like the UK may actually be becoming more consistent. I think I have one more slide. Oh yeah, I just wanted to couch all of this by saying that, returning to the topic of extreme weather and saying that these jet stream arguments, these arguments about whether Arctic amplification controls the jet stream waviness and extreme weather outbreaks, they're very separate from the very real extreme weather that we're seeing intensify because of sea ice loss around the polar latitudes. So scientists, it's really important to talk about the mid-latitudes. A lot of people live in the mid-latitudes, but we do see polar extreme weather absolutely occurring because of climate change, and particularly because of Arctic amplification and sea ice loss. So, and it often happens in ways that you might not expect initially. So here's a really interesting study that looked at sea ice loss and reindeer on the land, and you might not expect sea ice loss to directly relate to land. But it turns out as the loss retreats, we suddenly put the ocean, that warm ocean that was previously capped by the sea ice, in contact with the atmosphere, and it warms the atmosphere, but it also suddenly transfers loads of moisture to the atmosphere. And if that moves over the land, it can cause rain at really tricky times of year. So reindeer are really sensitive to this. Reindeer are really sensitive to unseasonable rain. They're really sensitive to what we call rain on snow events, but also rain on frozen ground events. And reindeer are kind of weird little guys. They lick lichen off the ground, right, for a lot of the year. And they rely on digging through snow to do that. So this is a great study that looked at an unseasonable rain event on snow in the Yamal Peninsula that's just east of Finland in Russia. And we had this unseasonable rain on snow event that was linked to sea ice decline. And it froze a layer of snow. And it made the reindeer unable to break through that snow. It was a hard layer of snow. And they just couldn't break through it to get to that lichen. And it was massive death. It's called mass death here, but it was literally millions of reindeer. And this happened twice. And this is exceptional, okay, because we have fossil records of reindeer. We know a rough history of reindeer. And this is really a drastic event that's directly linked to sea ice decline. It's an extreme event, and it's happening right now in the polar latitudes. And it's worth saying, actually, that as well as reindeer, a lot of species rely on smashing through snow to get to stuff. So a lot of birds of prey in the Arctic, like owls, hunt by diving through the snow and getting at things like lemmings that live in the snow. So as we bring about the unseasonable rain on snow events, we bring about the inability of lots of animals to hunt and to feed. There's also a really nice study here that links sea ice decline in the Barents Sea that's north of Norway to really unseasonable and extreme snowfall around Finland. And that is a nice example that's not linked to this wavy jet stream hypothesis, but it's linked to what I said earlier about a rapid and intense, I hate using the word flux, it's really sciencey, a rapid transport of moisture from the sea to the atmosphere that just dumped out in Finland and caused really extreme snowfall, not because of wavy jet streams or Arctic amplification, but just because the ocean was exposed by a peeling back of the sea ice in the Barents Sea. And the underlying cause of that is much more to do with warming and also the northward movement of Atlantic, warm, salty Atlantic water into the Arctic. And just one more thought that I like to bring up about all these themes about Arctic amplification and warming is that they really affect glaciers and terrestrial ice, land ice sheets. And in some ways, that's, I hate to say it as a sea ice scientist, but that's the real threat, because that's where we lock in things like sea level rise. So we talk about these things like the flux of heat and moisture to the atmosphere, and it's causing extreme precipitation, code for rain and snowfall in places like Svalbard that have these glaciers that respond on long time scales, and we have the capability to really wound on long time scales. So sea ice decline and Arctic amplification ties together a lot of these slow responding but very meanuful land ice themes that can be really dangerous looking out to 2100 and beyond. So that's all I've got to say about this topic. But if you have any questions about these themes, particularly about the jet stream, I can try and answer them for you. I'm very much a sea ice scientist and not a meteorologist, but please do shoot, and I'm sure Bimo would be happy to answer questions as well. Yeah, we'll get you a mic so that online people can hear.
Hi, thank you. A dumb question. I live in California, but I was born in Bangladesh. According to your latest science, what is the level of, how many meters of increase in sea level are we looking at in 2050?
In 2050?
Yeah.
Oh, I'm not a terrestrial glaciologist, and those are the folks that really handle this. But I think James could probably hazard an answer. 2050 is sooner than I am aware of the figures for, because it tends to accelerate as these big ice masses start to.
The reason I asked is because with 1 meter increase in sea level, large part of Bangladesh could go underwater, right?
For sure.
Just trying to get a sense of.
So the central estimate for 2100 is something like half a meter, but there's very wide uncertainty based on our emissions pathways, and also uncertainty in the science. The uncertainty bands are quite wide. For 2300, we're looking at, even if we hold temperatures to 2 degrees, we're looking at more like 1.5 meters in 2300 and beyond. But on 2050, ironically, the answer will be more certain, but I don't have it.
Hello, Beckwith. So, by my understanding, the jet streams exist because the Arctic is cold and the equator is warm and Antarctica is cold. So the jet streams, also the rotation of the Earth sets it up. So because we're greatly warming the Arctic, the jet stream has to change. So these papers that throw doubt that a warming Arctic isn't causing the jet streams to change don't make empirical sense at all. And also the question is when the Arctic is much, much warmer. So we lose all the sea ice, the ocean's heating in the summers, right? There's a lot more higher temperatures in the ocean and in the Arctic overall. What will the jet streams look like then?
Yeah, the jet stream is 100% changing because of Arctic amplification, right? So models fairly robustly simulate an equatorward move in the jet stream. But the specific question of factoring in that move, which, by the way, is underestimated in models. So they robustly simulate it, but not enough. Whether that results in a wavier jet stream, it remains unclear. But there's no way that we could warm the Arctic so much, shatter Arctic sea ice in summer, and not impact the jet stream, right? So the jet stream is changing, but the waviness and the relationship of that to extreme weather is still quite actively discussed.
Okay. My follow-up question is the loss of snow cover in the spring is as large an effect on Arctic amplification as the sea ice is, and yet you didn't mention that at all in your talk. So,
yeah.
Is there a reason why, or that's a different talk, I guess?
Well, it's not a totally different talk. So a lot of people talk about these jet stream breakdowns, and they talk about snow on the Siberian plain, particularly, and this thing called Ural blocking, which is where a loop of the jet stream comes down over Eurasia and kind of gets stuck and can develop persistent weather. And whether that is changing with climate change as that terrestrial snow recedes. And that snow is really important for a bunch of stuff. So it also impacts the timing with which the sea ice begins to melt, the extent of that snow cover and when it recedes. So you're right to bring it up, and it's absolutely a really important feature of the climate system. Again, I think it's just a topic of really intense debate whether changes in that Siberian plain snowfield are impacting jet stream variability. It looks like it. Oh, there you go.
So thank you very much for attending this event. I'd like to give our speakers another round of applause quickly. Our next event today will be at 11:30, and that will be on Indigenous peoples' food systems in the Arctic as game changers for climate action. So I hope to see you there. Thank you.